Nitrogen at 125 kPa, 30 degrees C, with a flow rate of 90 meters cubed per minute is mixed with CO2 at 200 degrees C, 125 kPa, with a flow rate of 40 meters cubed per minute. We're going to determine the final temperature and the rate of generation of entropy using the PG model, and then the IG model, and then the RG model. So first thing, we will want to go to flow states since it's a flow problem. And we're going to use the binary PG model since it's two different gases. Right, so test app, the first gas is nitrogen and the second one is carbon dioxide. And so we're going to treat state 1 as if it were just the nitrogen by itself. So we'll enter the parameters given, 125 kPa, 30 degrees Celsius, and a volume flow rate of 90 meters cubed per minute. And since we're treating this as if it were just the nitrogen, the mass fraction is going to be 1. And calculate. Get the rest of our properties. State 2 we'll treat as if it were just CO2. So again, we have 125 kPa for the CO2. It's given that the carbon dioxide is 200 degrees C and flowing at 40 meters cubed per minute. And so the mass fraction of fluid A, which was the nitrogen, is going to be 0 since this one is purely carbon dioxide. Right, calculate. Right, and state 3 is going to be our mixture. So P3 is going to be the same as P1 and P2 since they were the same. The volumetric flow rate is going to be a combination of the two since it's an additive property. So vol.1 plus vol.2. Same with the m dot. All right, and then the mass fraction of A is going to be m.1, which was the nitrogen state, divided by the total m dot for the mixture. So m.1 plus m.2. All right, and we can hit calculate, and we get that the temperature of the mixture is about 68 degrees Celsius. Right, and then for s.gen, we're assuming it's steady state, and we're assuming that it is adiabatic because it didn't mention anything about heat transfer. So using the energy equation, we can derive that s.gen is going to just be the difference in m dot times specific entropy. So s.gen is going to equal the final entropy, which is m.3 times S3 minus the initial, which is going to be m.1 times S1 plus m.2 times S2. So for s.gen, we get about 0.41 kilowatts per Kelvin. All right, the next part of the problem asks to find the mixture temperature using the IG and then RG model. So we could just repeat the whole process we just did in the binary IG model, but an easier way is to just hit super calculate and then copy and paste the code it generates. And then go to the binary IG model and its IO panel and just paste that code in. And then hit load, super calculate, and and go to state 3. Right, and we get again about 68 degrees Celsius, so pretty similar. Right, and then same thing for the RG model. You could just enter all the properties again, or simply paste this code in to easily compare answers. So paste, load, super calculate, and then state 3. We get about 68 again degrees Celsius.